A serious issue has surfaced aboard China's Tiangong space station, and the 3 astronauts currently living there no longer have a reliable return vehicle. Here's what's going on. You've likely heard the recent reports about orbital debris striking the Shenzhou 20 spacecraft. Because of that impact, its 3-person crew had to remain in orbit an extra 9 days, right alongside another trio of astronauts who had just arrived aboard Shenzhou 21 at the end of October. Tiangong can support 6 astronauts at once, but only for short stretches. It's really designed to sustain a crew of 3 for 6 months straight. So on November 14th, the Shenzhou 20 crew strapped into Shenzhou 21 and used it to return to Earth. But that move left the newly arrived astronauts without a dedicated spacecraft for emergency evacuation in case something like a fire or depressurization occurred. Not exactly an ideal position, so the big question became, what now? Fortunately, China reacted quickly. They've begun preparing a replacement Shenzhou spacecraft for launch earlier than planned. An airspace closure notice released November 17th indicates China is getting Shenzhou 22 and a Long March 2F rocket ready for liftoff around 11:10 p.m. Eastern on November 24th from the Jiuquan Satellite Launch Center in the Gobi Desert. China's Human Spaceflight Agency hasn't yet officially confirmed the mission, but CCTV reported that preparations are already in progress, noting Shenzhou 22 will deliver a full load of supplies and station hardware. This one will be an uncrewed flight. An official from China's manned space program told CCTV that the Shenzhou 22 launch mission has begun and that teams are already testing spacecraft systems, rocket components, and loading cargo. The idea is simple. Launch Shenzhou 22 early so Tiangong regains an emergency lifeboat. That way, the Shenzhou 21 crew can safely finish their full 6-month mission and return home around April 2026. China previously stated that a backup Long March 2F rocket and Shenzhou spacecraft would always remain nearly ready at Jiuquan in case anything went wrong on Tiangong, with the capability to launch within about 8.5 days under ideal conditions. This launch, however, will occur about 20 days after the Shenzhou 20 damage was discovered. How fast a backup mission can fly depends on several factors. Launch pad readiness, one of which had just supported Shenzhou 21, weather conditions, range safety, orbital mechanics, and the status of the spacecraft and rocket. Even if everything is technically ready, the launch must still align with Tiangong's orbit, which can add additional days. Another big question people have is whether China can remove the damaged spacecraft from Tiangong. Since 2021, China's Shenzhou missions have been ferrying 3-person crews to the station for 6-month rotations. But this is the first time a Shenzhou vehicle has been left in orbit while its crew returned home aboard a different spacecraft. The debris-damaged Shenzhou 20 now needs to be either repaired in orbit or removed entirely. If China doesn't address it, future missions would run into problems because Tiangong always needs at least one docking port open for incoming Shenzhou vehicles. Technically, Shenzhou 20 is still docked and accessible, but China has already declared it unsafe for crewed re-entry. In a statement on November 14th, they explained why. After photo inspections, design reviews, simulations, and wind tunnel testing, analysts concluded that Shenzhou 20's return capsule window glass has developed a small crack, likely from a debris strike, and no longer meets safety standards for bringing astronauts back to Earth. For now, officials say the spacecraft will remain in orbit to support related experiments. Even a tiny fracture in the heat-resistant outer glass of a viewport can expand during re-entry. If the pane failed, the layers beneath could be exposed to extreme plasma heating, potentially compromising the window and risking a dangerous loss of pressure inside the capsule. If the damage is ultimately deemed too serious to repair, a likely outcome is that China will undock Shenzhou 20 from Tiangong and command it to perform a controlled re-entry over a remote region of the Pacific Ocean. They've already stated plans to deorbit the spacecraft at a later date. So that's the latest update on the incident. China's Shenzhou complications mark the second time in just 2 years that astronauts have ended up effectively stranded on a space station without their own return craft. We saw something similar last year with Boeing's Starliner. NASA astronauts Butch Wilmore and Suni Williams flew the capsule to the International Space Station in June 2024 for what was supposed to be roughly a 10-day mission. Starliner reached orbit, but encountered helium leaks and troublesome thrusters along the way. Because of those issues, NASA decided to keep Wilmore and Williams aboard the ISS longer than planned. The Starliner capsule eventually returned to Earth uncrewed that September. In the end, both astronauts were reassigned to a long-duration ISS mission and didn't make it home until March 2025. This time aboard a SpaceX Crew Dragon. Space analyst Oberg noted that both the Boeing situation and the Shenzhou incident were fortunate outcomes in the sense that things could have gone far worse. To China's credit, it's impressive how quickly they made a decision and brought their astronauts home within days. But these events are also a clear wake-up call. We urgently need a dedicated international space rescue capability. Those dramatic headlines about stranded astronauts highlight an uncomfortable truth. We currently don't have a reliable go-get-them option if a spacecraft fails in orbit. Here on Earth, rescue teams can reach all kinds of dangerous or remote locations. Sailors adrift at sea, climbers injured high in the mountains, even survivors of plane crashes in isolated regions. But in space, there is no rapid response rescue system. The hard-won lessons from Apollo, Skylab, and the shuttle era about the importance of in-space rescue have faded from memory. And that's happening at a time when more astronauts than ever, from more nations and increasingly flying on commercial vehicles, are heading into orbit. It's a gap we shouldn't ignore much longer. The concept of rescuing a crew stranded in orbit has been studied for decades. The core idea is straightforward. The crew only faces danger if both their spacecraft and the rescue vehicle fail. That means even a spacecraft with 90% reliability could give astronauts a 99% survival chance if there's a backup rescue craft also with 90% reliability. This matters because making a spacecraft extremely reliable is incredibly expensive. For example, taking a vehicle from 99% reliability to 99.9% reliability costs far more than reaching 99% in the first place. NASA has even considered launching crews on rockets with reliability as low as 77%. With a rescue system that works 90% of the time, crew survival could jump to somewhere between 91% and 99.6%. There are two main concepts behind space rescue systems. One treats the rescue craft like a lifeboat, a small vehicle astronauts could board to return home. The problem is that it's extremely difficult to fit people and critical systems into something that small. The second approach treats rescue more like a parachute. Each astronaut leaves the damaged spacecraft individually using a personal re-entry device. The challenge is that a person-sized system must survive brutal re-entry conditions, extreme heat, enormous pressure, and decelerating from orbital speeds, all while keeping the astronaut alive. Fortunately for recent crews, these incidents occurred after they had already reached their space stations. Had the spacecraft gotten into serious trouble beforehand, the story could have ended very differently. Most space rescue today relies on what's called self-rescue. The crew must save themselves using whatever equipment is already available because launching a second spacecraft quickly is extremely difficult. To rescue one spacecraft with another, several things have to go right. The damaged vehicle must keep the crew alive long enough for help to arrive. The rescue craft needs to be able to launch on very short notice, and the launch cannot be heavily restricted by weather or orbital timing. Rescue becomes far more feasible if the damaged vehicle can dock with another craft that already provides life support. That's exactly what saved the Apollo 13 astronauts. Their crippled spacecraft remained attached to the lunar module, which served as a temporary lifeboat until they could return home. In low Earth orbit, astronauts can sometimes use the International Space Station as a safe haven. but only if the troubled spacecraft can adjust its orbit enough to reach it. After the Columbia accident, many wondered whether the shuttle could have flown to the ISS for rescue. The answer is no. Columbia launched into a completely different orbital tilt, and changing that tilt would have required nearly all of its fuel, leaving no way to reach the station. Some spacecraft are naturally better suited for rescue than others. SpaceX's Crew Dragon, for example, is an excellent candidate because of its proven reliability, but even older vehicles like Russia's Soyuz are extremely effective thanks to their ability to launch quickly, operate in harsh weather, and remain docked for months, ready to bring astronauts home in an emergency. The Space Shuttle, by comparison, required longer preparation times and needed far better weather conditions, although it could carry many more people. That meant Soyuz was more practical for emergencies, but it lacked the capacity to return large ISS crews. If a 7-person shuttle crew had ever been stranded at the ISS, NASA would have needed 4 separate Soyuz launches to rescue everyone, an incredibly difficult operation to coordinate. When multiple rescue flights are required, the math becomes a real problem. The more launches needed, the higher the reliability each one must have to keep the total survival odds high. This is why NASA preferred the concept of a single spacecraft capable of carrying all 7 ISS crew members home at once. It avoids the steep rise in risk that comes with depending on several rescue attempts. Whenever engineers discuss space rescue systems, the debate always comes down to a trade-off between risk and cost. Rescue systems for space are typically complicated, expensive, and difficult to test. So when the primary spacecraft program runs into financial trouble, project delays, or technical challenges, the rescue requirements are often among the first to be questioned. Critics ask why so much money should be spent on a system that might only be used if the main spacecraft fails completely. Others argue that instead of building a rescue system, it might be better to invest more into making the primary spacecraft reliable enough that no backup is necessary. A common comparison people make involves commercial airplanes. Early aircraft carried parachutes, but modern airliners do not. Some use this argument to claim astronauts shouldn't need escape or rescue systems either, but human spaceflight is far more dangerous than any commercial flight on Earth, and that risk is the strongest reason rescue systems are still necessary. The dangers are partly due to how young the technology still is. Aviation has had decades of refinement, while human spaceflight has had far fewer flights and far fewer generational improvements. Spacecraft also face extreme conditions. To reach orbit, they must travel thousands of miles per hour and burn enormous amounts of fuel. Engineers must design spacecraft as lightweight as possible, sometimes with walls so thin that if you scaled them down to the size of a soda can, they would be thinner than the can itself. The space environment adds even more risk. There's no air, so any leak is immediately dangerous. Materials behave differently in a vacuum. Temperature swings can be massive, from blistering sunlight to freezing darkness just inches apart. During launch, the spacecraft endures intense aerodynamic stress. During re-entry, the exterior faces temperatures hotter than molten metal while being slammed by heavy air pressure. And in orbit, spacecraft are constantly exposed to radiation and tiny fragments of space debris traveling at lethal speeds. Even the shuttle's windows and radiators were damaged over time.